It's late, or maybe just quiet enough to feel like it is. The kind of quiet where your thoughts slow down just enough to notice the details you usually miss. And tonight, we're going to look at something familiar. Something that most people feel they already understand, but rarely stop to truly examine. Because when it comes to NASA, the story most of us know is surprisingly clean, surprisingly structured, and maybe a little too neat. Before we go any further, take a second to settle in, wherever you are listening from. And if you enjoy exploring topics like this, slowly, carefully, without jumping to conclusions, consider subscribing to the channel. It helps more than you think. And I'm always curious, where in the world are you listening from right now? Now, NASA. Officially, it is the United States Civilian Space Agency, founded in 1958 during the height of the Cold War. Its mission, at least on paper, is straightforward. Explore space, advance science, and expand human knowledge. Over the decades, it has given us some of humanity's most iconic achievements: the Apollo 11 moon landing, the Hubble Space Telescope, the Mars rovers, and an endless stream of data about the universe beyond our planet. That's the official narrative. And to be clear, it is backed by an enormous amount of evidence, documentation, and collaboration with scientists all over the world. Thousands of engineers, researchers, and independent observers contribute to and verify much of what NASA produces. The mainstream explanation is not something easily dismissed, and it shouldn't be. But here's where things begin to get interesting. Not because of what we know, but because of how much we don't question. NASA operates at the edge of human capability. It deals with environments that most of us will never experience directly. Deep space, extreme radiation, near total vacuum. And because of that, almost everything we know about these places comes to us filtered through instruments, through data processing, through interpretation. We are, in a sense, trusting a system to describe a reality we cannot personally verify. And that's not inherently suspicious. It's simply the nature of modern science. But it does open the door to a quieter, more subtle question. Not, is NASA hiding something? That's too blunt, too simplistic. A better question might be, how much of what we believe about space is shaped by interpretation rather than direct experience? For example, consider the images we see from deep space. The breathtaking colors of nebulae, the glowing clouds of distant galaxies. Officially, many of these images are composites, constructed from different wavelengths of light, including infrared and ultraviolet, which are invisible to the human eye. Scientists assign colors to represent these wavelengths, creating visuals that are both informative and, in a sense, artistic. The mainstream explanation is clear. These images are not meant to deceive, but to translate complex data into something we can understand. And that makes sense. But it also raises a subtle point. If what we are seeing is already an interpretation, then how close is it to what is actually there? Not in a conspiratorial sense, but in a philosophical one. Are we seeing space as it is, or as we are capable of perceiving it? And once you start thinking along those lines, you begin to notice patterns. Not inconsistencies exactly, but areas where the story feels incomplete. Take the early days of NASA, for instance. The agency was born out of the National Advisory Committee for Aeronautics, transitioning rapidly during a time of intense geopolitical pressure. The space race was not just about exploration, it was about demonstrating technological superiority. Every launch, every mission carried symbolic weight. From a mainstream perspective, this urgency accelerated innovation. It pushed engineers to achieve what might have otherwise taken decades, and there's plenty of evidence to support that. But from another angle, it also created an environment where perception mattered just as much as reality. Success needed to be visible. progress needed to be undeniable. And in that kind of environment, the line between communication and presentation can become blurred. Again, this isn't a claim of deception. It's an observation about human systems under pressure. Now consider something else. NASA, despite being a government agency, operates with a surprising level of opacity in certain areas. Not total secrecy, far from it, but selective transparency. Some data is released publicly, some is delayed, and some is filtered through layers of analysis before anyone outside the agency sees it. The mainstream explanation here is practical. Raw data from space missions is often complex, incomplete, or easily misinterpreted. Releasing it without context could lead to confusion or misinformation. So it is processed, verified, and then shared. That makes sense. But it also means that, by the time information reaches the public, it has already been shaped. Not necessarily altered, but framed. And framing, even when done with good intentions, influences how something is understood. So the question becomes, how much of our understanding of space is based on raw discovery, and how much is based on curated interpretation? And then there are the anomalies, not the dramatic, headline-grabbing kind, but the quieter ones. Data that doesn't quite fit expectations, signals that are difficult to explain, observations that are acknowledged, but not deeply explored in public discussions. In most cases, the explanation is simple. Science is an ongoing process. Not every anomaly leads to a breakthrough. Many are resolved with further study or quietly set aside as noise or error. But occasionally, these anomalies linger. Not enough to overturn existing models, but enough to suggest that the models themselves might be incomplete. And this is where things shift from known science into something more speculative, but still grounded. Because if there are gaps in our understanding, and if those gaps are filtered through systems that prioritize clarity and consensus, then it's possible that certain questions never fully surface. Not because they are being hidden, but because they don't fit neatly into the narrative being communicated. And NASA, as the primary storyteller of space exploration, plays a central role in shaping that narrative. Think about it this way. If humanity's understanding of the universe is like a map, NASA is one of the main cartographers. They are drawing the outlines, labeling the features, deciding what is emphasized and what is left in the background. And maps, by their nature, are not the territory. They are representations. So as we move forward, what we're really exploring is not just NASA itself, but the space between what is known, what is shown, and what might still be waiting in the margins. Because the most interesting questions are rarely the obvious ones. They're the quiet ones, the ones that don't demand answers, but instead invite closer observation. And tonight, that's exactly what we're going to do. We're going to take our time, look at the history, the data, the patterns, start with what is widely accepted, and then gently, carefully, examine where things become less certain. Not to jump to conclusions, but to understand the edges of the story a little better. Because sometimes the most revealing details aren't hidden behind secrecy. They're simply overlooked. As we move a little deeper into this, it helps to slow down and focus on one of the most foundational chapters in NASA's story. Not the polished version most people remember, but the underlying structure that made everything possible in the first place. Because long before the moon landings, long before the iconic images and carefully narrated missions, NASA was something else entirely. A rapidly assembled system built during a time when urgency often came before clarity. When NASA was officially established in 1958, it wasn't starting from nothing. It inherited knowledge, infrastructure, and personnel from the National Advisory Committee for Aeronautics, but more importantly, it absorbed expertise from a much more complex and, at times, controversial source. After World War II, the United States initiated programs like Operation Paperclip, bringing over German engineers and scientists, many of whom had been involved in advanced rocket development during the war. From a mainstream historical perspective, this decision was pragmatic. The technology developed in Germany, particularly the V2 rocket, was far ahead of anything else at the time. Figures like Wernher von Braun became central to the United States' early space ambitions, eventually playing a leading role in NASA's rocket programs. Without this transfer of knowledge, it's widely accepted that the timeline of space exploration would have been significantly delayed. And again, this is well documented, openly acknowledged history. There's no secrecy in the fact that NASA's early advancements were built, in part, on foundations established during wartime. But here's where the story becomes more layered. When you look at how quickly progress unfolded, from early experimental rockets to launching humans into orbit, and then to landing on the moon within just over a decade, it raises a natural question. Not a skeptical one, but a curious one. How much of this progress was truly new? And how much of it was an extension of technologies and ideas that were already further along than most people realized? The mainstream explanation emphasizes rapid innovation, driven by competition, particularly during the space race. The United States and the Soviet Union were pushing each other forward at an unprecedented pace. Each milestone achieved by one side became a challenge for the other to surpass. In that environment, breakthroughs were not just encouraged, they were necessary. And yet, even within that explanation, there are subtle gaps. Not contradictions, but areas where the details are less frequently discussed. For instance, early rocket science was not just about engineering. It was about understanding environments that had never been directly experienced before. High-altitude physics, microgravity effects, long-duration exposure to space conditions. These were largely theoretical fields. And while test flights and unmanned missions provided data, the leap from theory to reliable human spaceflight was enormous. So when NASA began launching astronauts under programs like Project Mercury and later Project Gemini, the official narrative frames these as carefully staged steps, incremental progress, each mission building on the last. Which is true. But if you examine the timeline closely, the speed of that progression is striking. Within a relatively short period, NASA went from testing basic orbital flight to performing complex maneuvers like docking spacecraft, conducting spacewalks, and preparing for lunar missions. The accepted explanation is that necessity accelerated capability. And historically, that holds up. Human innovation tends to move fastest under pressure. Still, it invites a quieter line of thought. Were there aspects of this knowledge that were already more developed than publicly presented? Not in a hidden or conspiratorial sense, but in the way institutions sometimes simplify narratives for clarity. Because complexity doesn't always translate well to public understanding. And during the 1960s, NASA wasn't just solving engineering problems, it was also communicating progress to a global audience. And that audience needed to believe in a clear, understandable story of advancement. Now, let's shift slightly. Away from rockets and towards something less tangible, but just as important, data. NASA's missions have always relied on vast amounts of information, telemetry, sensor readings, environmental measurements. This data is the backbone of every decision, every conclusion, every claim about what is happening in space. From a mainstream perspective, this data is rigorously collected, analyzed, and cross-verified. Independent scientists often have access to portions of it, and many findings are published in peer-reviewed journals. There is a system of accountability built into the process. But at the same time, not all data is equally accessible. Some of it remains within internal systems, some is released only after processing, and some is summarized rather than shared in raw form. Again, this is not unusual. In fact, it's standard practice in many scientific fields. Raw data can be noisy, incomplete, or misleading without proper context. But it does create an interesting dynamic. The version of reality that reaches the public is not the raw signal, it is the interpreted signal. An interpretation, by its nature, involves choices. What to highlight, what to consider noise, what to revisit, and what to move past. Most of the time, these choices are guided by established scientific frameworks, models that have been tested and refined over years, even decades. But what happens when data doesn't fit those models perfectly? In many cases, it leads to new discoveries, adjustments to theory, refinements in understanding. But in other cases, it leads to ambiguity. And ambiguity is not something that institutions communicate easily, especially institutions like NASA, which operate under public scrutiny and political oversight. Clarity is often prioritized because clarity builds confidence. So the question begins to take shape, not as a challenge to NASA's credibility, but as an exploration of its structure. Is it possible that some uncertainties are smoothed over in the process of communication? Not removed, not hidden, but simplified? And if so, what does that mean for how we perceive the boundaries of what is known? Because when you step back and look at it, NASA is doing something extraordinary. It is attempting to describe environments that are fundamentally outside human experience, using tools and models that are, at their core, human constructs. And that process, no matter how precise, will always involve a degree of interpretation. Now, none of this suggests deception. It suggests something more subtle and perhaps more interesting. That the story of space exploration is not just about discovery, it's about translation. Translating data into understanding. Translating complexity into clarity. Translating the unknown into something we can begin to grasp. And in that translation, details can shift, not intentionally, but inevitably. So as we continue, what we're really looking for are those moments where the translation becomes visible, where the gap between raw observation and communicated understanding reveals itself, even slightly. Because those gaps, small as they may be, are often where the most interesting questions begin. As we continue, it becomes useful to shift our attention toward one of the most iconic and most discussed chapters in NASA's history. Not because it is mysterious in the obvious sense, but because it represents a moment where certainty and uncertainty exist side by side in a way that is easy to overlook. The Apollo 11 moon landing is often treated as a completed story, something settled, documented, and archived. And in many ways, it is. The mainstream explanation is supported by mission logs, telemetry data, independent tracking from observatories around the world, and physical samples, lunar rocks that have been studied for decades. From a scientific standpoint, the evidence is substantial. The missions under the Apollo program are among the most thoroughly documented events in modern history. Thousands of people were involved, from engineers to contractors to international observers. The level of coordination required alone makes the idea of fabrication highly improbable. That is the mainstream position, and it is one that holds up under scrutiny. But what makes this chapter worth examining is not whether it happened, it's how it is understood. Because when you look closely, the moon landings exist at a unique intersection of technology, communication, and perception. They were not just scientific missions, they were global events, broadcast in real time to millions of people, at a moment when television itself was still evolving as a medium. And that introduces a subtle layer to the story. The footage that most people associate with the moon landing, the grainy black and white images, the slow, almost dreamlike movements of Neil Armstrong, was transmitted across an enormous distance, processed through multiple systems, and then converted into a format that could be displayed on televisions of the time. The mainstream explanation for the unusual visual quality is entirely technical. The cameras used on the lunar surface were designed for efficiency and reliability, not cinematic clarity. The signal was compressed, transmitted, received, and then refilmed off a monitor for broadcast. That chain of translation is well understood. But it also means that what the public experienced was not a direct window into the event. It was a representation of it, a version shaped by the limitations and requirements of the technology available at the time. Now, again, this is not unusual. Every form of communication involves some level of mediation. But in this case, the distance between the original event and the received image was greater than anything humanity had attempted before. And that raises an interesting point. If the primary experience of such a historic moment is mediated through layers of technology, then the perception of that moment is inherently shaped, not just by what happened, but by how it was presented. From a mainstream perspective, this doesn't change the underlying reality. The event occurred, and the footage is simply a reflection of the technological constraints of the era. But from a more analytical perspective, it introduces a gap, a small one, but a meaningful one. The difference between the event itself and the experience of the event. And within that gap, questions naturally arise, not about authenticity in a broad sense, but about interpretation. For instance, consider the environmental conditions on the moon, the absence of atmosphere, the way light behaves without scattering, the extreme contrasts between shadow and illumination. These factors create visuals that can appear unusual to someone accustomed to Earth-based environments. Mainstream science explains these differences clearly. Shadows appear sharper because there is no air to diffuse light. The sky appears black even during daylight because there is no atmosphere to scatter sunlight. Temperatures vary dramatically depending on exposure to direct sunlight. All of this is consistent with physics. And yet, when people first saw the images and videos from the moon, many of these characteristics felt unfamiliar, not incorrect, but different enough to prompt questions. And those questions over time evolved into broader discussions, some grounded, some less so, about the nature of the missions themselves. But if we set aside the more extreme interpretations, what remains is something quieter and more subtle. The realization that even in one of the most well-documented events in human history, our understanding is still mediated, still dependent on interpretation, on translation, on context. And this is where the pattern we've been noticing begins to repeat. NASA provides data, images, explanations. These are based on rigorous science and engineering, but the way this information is experienced by the public is always one step removed from the original source. And that step, however small, introduces the possibility for variation, not necessarily error, but difference. Now, let's consider another aspect of the Apollo missions that receives less attention. After Apollo 17 in 1972, human missions to the moon stopped. Not paused briefly, but stopped entirely, for decades. The mainstream explanation is practical. The cost of the Apollo program was enormous. Political priorities shifted. Public interest declined after the initial excitement. NASA redirected its focus toward other goals, such as the space shuttle and later orbital research. All of this makes sense within the context of government decision-making and budget allocation. But when viewed from a different angle, it introduces an intriguing question. If the technological capability to reach the moon existed in the early 1970s, why did it not continue to develop in a more continuous way? Technology, in most fields, tends to progress incrementally. Capabilities expand, become more efficient, more accessible over time. And yet, in the case of lunar missions, there is a noticeable gap. A pause that lasted far longer than many would have expected. Of course, there are explanations for this. The Saturn V rocket, for example, was incredibly powerful, but also complex and expensive to maintain. Recreating that capability is not as simple as restarting production. It involves rebuilding entire supply chains, retraining personnel, and redesigning systems with modern standards. Still, the gap remains. And it's not a contradiction. It's a point of curiosity, because it highlights something important about how progress is perceived versus how it actually unfolds. From the outside, it can seem like a step backward. From the inside, it may be a shift in direction, influenced by factors that are not immediately visible. And that brings us back to the broader theme. NASA's history is not just a sequence of achievements. It is a series of decisions. Choices about what to pursue, what to prioritize, and how to communicate those priorities. And within those choices, there are always layers. Some are technical, some are political, some are simply practical, but together, they shape the narrative. So as we move forward, what we're really doing is not questioning the events themselves, but examining the space around them. The context, the presentation, the transitions. Because sometimes, understanding the edges of a story reveals just as much as the story itself. As we continue moving forward, the focus begins to shift away from singular historic events and towards something more continuous. Something that doesn't belong to one mission or one decade, but quietly spans across nearly everything NASA does. Because beyond rockets, beyond astronauts, beyond even the idea of space travel itself, there is a deeper layer that rarely gets discussed in detail. And that is how NASA observes the universe, and how those observations are turned into what we eventually understand as reality. At the center of this is one of the most well-known instruments ever placed into orbit, the Hubble Space Telescope. Launched in 1990, Hubble has captured some of the most detailed images of distant galaxies, nebulae, and cosmic structures ever seen. From a mainstream scientific perspective, its role is clear. It allows astronomers to observe wavelengths of light that are partially or completely blocked by Earth's atmosphere, providing a clearer and more expansive view of the universe. And the data it produces has led to major discoveries. The expansion rate of the universe, evidence supporting dark energy, detailed measurements of distant stars. All of these are tied, in part, to observations made by Hubble. So at first glance, this seems straightforward. A highly advanced instrument collects light from distant objects, converts that light into data, and that data is analyzed to produce images and conclusions. But as with everything we've been exploring, the interesting part is not just what happens, but how it happens. Because Hubble does not see in the way human eyes see. It doesn't capture a scene the way a camera on Earth would. Instead, it records specific wavelengths of electromagnetic radiation, often far beyond the visible spectrum. Infrared, ultraviolet, and other bands of light are detected separately, measured, and then processed. The mainstream explanation is that this allows scientists to extract more information than would be possible with visible light alone. Different wavelengths reveal different physical properties, temperature, composition, motion, and that's entirely accurate. But it also means that the images we see, the iconic, almost surreal visuals of deep space, are not direct photographs. They are constructed representations. Data mapped into a visual format that makes sense to us. Colors are assigned. Contrast is adjusted. Features are emphasized. Again, not to mislead, but to translate. And this brings us back to a recurring pattern. What we perceive as a view of space is, in reality, a layered interpretation of data. Now, this doesn't diminish the validity of the science. If anything, it highlights the complexity of it. But it does introduce an important nuance. The universe we see through NASA's images is not the universe as it would appear to human eyes. It is the universe as interpreted through instruments, algorithms, and decisions about how to present information. And that distinction, while subtle, is worth sitting with for a moment. Because it means that even at the highest levels of scientific observation, there is a translation layer between reality and perception. Now, let's take this a step further. Beyond Hubble, NASA operates a network of observational tools, satellites, probes, telescopes, each designed to collect specific types of data. The James Webb Space Telescope, for example, focuses heavily on infrared wavelengths, allowing it to peer through cosmic dust and observe objects that are otherwise obscured. From a mainstream standpoint, this is simply an expansion of capability. Different instruments provide different perspectives, and together they create a more complete picture. But notice what this implies. There is no single, unified view of the universe. There are multiple layers, each revealing something different depending on how it is observed. And when those layers are combined, the result is not just discovery, it is synthesis, a constructed understanding built from multiple streams of data. Which leads to a quiet but important question. If our understanding of space is built from multiple interpretations of data, how do we decide which interpretation is most accurate? In science, the answer is usually consensus. Models are tested, predictions are made, results are compared. Over time, certain explanations become widely accepted because they consistently match observations. And this system works remarkably well, but it is not immune to limitation. Because consensus, by its nature, tends to favor explanations that fit within existing frameworks. New ideas are accepted, but often only after significant evidence accumulates. And in the meantime, data that doesn't fit neatly into those frameworks can exist in a kind of quiet uncertainty. Not ignored, but not fully resolved either. This brings us to one of the more subtle aspects of NASA's role, not just as an observer, but as an interpreter. NASA doesn't just collect data, it also decides how that data is processed, which findings are highlighted, and how those findings are communicated to the public. And again, this is not unusual. Every scientific institution operates this way to some extent. But when the subject is something as vast and inaccessible as the universe, the impact of those decisions becomes more significant. Because for most people, NASA is not just a source of information, it is the source. Now, let's pause for a moment and consider something that often goes unnoticed. Space, as described by NASA, is filled with concepts that are difficult to visualize directly. Dark matter, dark energy, black holes, cosmic inflation. These are not objects we can see in a traditional sense. They are inferred from data, mathematical models, gravitational effects, patterns in radiation. The mainstream explanation is that these concepts are necessary to explain observations that would otherwise remain unresolved. For example, galaxies rotate in ways that suggest there is more mass present than we can detect. Dark matter is the proposed solution, and it fits the data, but it is also, by definition, something that has not been directly observed. And that's where the pattern becomes especially clear. Even at the highest levels of astrophysics, our understanding is built not just on observation, but on interpretation of observation. Now, this is not a flaw. It is how science progresses. Hypotheses are formed, tested, refined. But it does mean that the story of the universe is still being written. And NASA, through its instruments and its communication, plays a central role in writing that story. So as we continue, what we're beginning to see is a consistent structure. Data is collected, processed, interpreted, and then presented. At each step, the information becomes more accessible, but also more shaped. And the further it moves from the raw signal, the more it reflects not just what was observed, but how it was understood. Which brings us back to the core idea we've been quietly following. Not that anything is being hidden, but that everything is being translated. And in that translation, there is always room for nuance, for uncertainty, for questions that don't have immediate answers. Because the universe, as vast as it is not something we have fully mapped. Not yet. And perhaps the most interesting part of NASA's story is not what it has already revealed, but what it is still trying to understand. As we move further into this exploration, it becomes helpful to shift from distant space, back towards something closer, something that exists just on the edge of our everyday awareness, yet is still shaped almost entirely by NASA's interpretation. Because while deep space captures the imagination, much of NASA's most continuous and influential work actually happens much closer to home, right here, in orbit around Earth. Satellites, observational platforms, instruments that quietly circle the planet, collecting data about weather patterns, atmospheric composition, ocean temperatures, and long-term climate trends. Unlike the dramatic milestones of the Apollo program, these systems don't usually dominate headlines. They operate in the background, constant and methodical, building an ongoing picture of Earth as a dynamic, evolving system. From a mainstream perspective, this is one of NASA's most valuable contributions. Agencies like NASA, along with partners such as NOAA, provide critical data that informs everything from daily weather forecasts to long-term climate models. Without this data, modern meteorology and environmental science would be significantly less precise. And importantly, much of this information is publicly available. Researchers around the world use NASA's datasets to conduct independent analyses, publish findings, and refine models. There is a broad scientific ecosystem built around this flow of information. But just like with deep space observations, the interesting layer isn't the existence of the data, it's the process that turns that data into something we understand. Because satellites don't see Earth the way we do from the ground. They measure radiation across different wavelengths, detect subtle variations in temperature, track chemical signatures in the atmosphere. The raw data is complex, often abstract, and not immediately meaningful without interpretation, so it is processed. Algorithms convert measurements into visual maps. Color gradients are applied to represent temperature differences. Patterns are identified, emphasized, sometimes smoothed to reduce noise. Over time, these processed outputs become the images and graphs that shape how we think about the planet. The mainstream explanation is straightforward. This processing is necessary. Without it, the data would remain inaccessible to most people, including many scientists who rely on standardized formats for analysis. And again, that makes sense. But it also introduces a familiar pattern. What we perceive as a view of Earth from space is not a direct photograph in many cases. It is a constructed representation, built from layers of measurement and interpretation. Now, this doesn't mean the data is inaccurate. It means that understanding it requires trust in the systems that process it. And that trust is generally well placed. The methods used are documented, tested, and refined over time. Independent verification exists. Still, there is a subtle implication worth considering. If most people experience Earth's global systems through processed data, through maps, models, and visualizations, then their understanding is shaped not just by the data itself, but by how that data is presented. For example, consider global temperature maps. The colors used, deep reds for warmer regions, blues for cooler ones, create an immediate visual impression. Patterns become visible at a glance. Trends can be identified quickly. But those colors are choices. They are part of the translation process. Different scales, different ranges, slightly different processing methods can lead to different visual impressions, even when the underlying data is similar. Again, not misleading, just interpretive. And this brings us to a broader idea that extends beyond Earth observation. NASA operates in environments where direct human perception is limited or impossible. Whether it's the vacuum of space or the upper layers of the atmosphere, most of what is studied cannot be experienced firsthand by the general public. So everything must be translated. And translation, no matter how precise, is never completely neutral. It involves decisions, technical, methodological, sometimes even aesthetic. Now let's take this one step further. In addition to observing Earth's present state, NASA is deeply involved in modeling its future. Climate projections, for instance, rely on complex simulations that incorporate vast amounts of data. These models attempt to predict how systems will evolve over years, decades, even centuries. The mainstream scientific position is that these models are based on the best available data and understanding. They are continuously updated, compared against observations, and refined to improve accuracy. And they have proven useful. Predictions about trends, such as rising global temperatures or shifting weather patterns, have, in many cases, aligned with observed changes. But modeling the future is inherently different from observing the present. It requires assumptions about variables, about interactions, about how systems respond to change. And while these assumptions are grounded in data, they are still assumptions. So when NASA communicates projections, what we are seeing is not just data, it is a scenario, a carefully constructed possibility based on current understanding. And this introduces a different kind of gap, not between observation and perception, but between prediction and reality. Most of the time, this gap is acknowledged. Scientific reports often include ranges, uncertainties, confidence levels. But in broader communication, summaries, visuals, public-facing explanations, these nuances can become less visible, not intentionally, but as a result of simplification. And once again, we return to the same underlying structure. Data becomes information. Information becomes understanding. Understanding becomes narrative. And at each step, complexity is reduced just enough to make it accessible. But in that reduction, some details inevitably fade into the background. Now, this isn't unique to NASA. It's a characteristic of all large-scale scientific communication. But NASA operates on a scale that makes these dynamics especially significant. Because it is not just describing isolated phenomena, it is describing entire systems, the Earth, the solar system, the universe. And for most people, these descriptions form the foundation of how reality itself is understood. So as we continue, what we're really exploring is not whether NASA's data is correct, but how that data becomes the reality we perceive. Because perception, especially when it is mediated through complex systems, is never just about what is there. It's about how it is revealed. And sometimes the way something is revealed can be just as important as the thing itself. As we continue, it becomes useful to turn our attention to something that feels, at first, more grounded, more tangible, and yet, in its own way, just as layered as everything we've explored so far. Because while satellites observe Earth and telescopes look outward into deep space, there is another environment where NASA operates continuously, one that exists in between. Not quite Earth, not quite space in the distant sense, but a threshold where both begin to blur. Low Earth orbit. This is where the International Space Station quietly circles the planet, moving at speeds of roughly 28,000 kilometers per hour, completing an orbit every 90 minutes. From a mainstream perspective, the station represents one of the most successful examples of international cooperation in scientific history. Built and maintained by agencies including NASA, Roscosmos, ESA, and others, it serves as a laboratory for studying microgravity, human physiology, and long-duration spaceflight. And unlike deep space missions, the ISS is something we can, in a limited way, observe directly. It is visible from the ground at certain times, a small, bright object crossing the sky with steady motion. Its orbit is tracked publicly. Its presence is not abstract. From the mainstream standpoint, this makes it one of the most transparent aspects of NASA's operations. Live video feeds are often available. Astronauts communicate with Earth regularly. Experiments conducted aboard the station are documented and shared. And yet, even here, even in this relatively accessible environment, the same pattern begins to emerge. Because what we see of the ISS, through video, images, and communication, is still mediated. Cameras positioned inside modules, external views from mounted systems, carefully selected angles that present life aboard the station in a coherent, understandable way. Again, this is entirely practical. There is no expectation that every moment, every perspective would be broadcast in raw form. The station is a working environment, not a continuous open feed. But it does mean that our understanding of life in orbit is shaped by what is shown. And that brings us to a subtle but interesting point: microgravity. One of the defining features of the ISS is the apparent weightlessness experienced by astronauts. Objects float, movements are slow and controlled, liquids form into spheres. From a scientific perspective, this is explained by the concept of continuous free fall. The station is constantly falling toward Earth, but moving forward fast enough that it keeps missing it, creating the effect of weightlessness. This explanation is well established and supported by physics. But for most people, microgravity is something experienced only through video. It is not something we can verify directly in our daily lives, and that introduces, once again, a layer of interpretation. Not because the phenomenon is questionable, but because our understanding of it relies on mediated observation. Now consider how this environment is presented. Astronauts floating effortlessly, tools drifting gently through modules, experiments unfolding in slow motion. These visuals are consistent, repeated, and widely recognized. But they are also curated. Not in a misleading way, but in a way that emphasizes clarity. The most illustrative moments are shown. The most understandable demonstrations are highlighted. And this makes sense. But it also means that what we perceive as the reality of life in orbit is, in part, a distilled version of a much more complex environment. Now, let's take this a step further. Communication. Signals from the ISS travel through a network of satellites, ground stations, and relay systems before reaching the public. There are delays, compression, occasional interruptions. The system is robust, but not instantaneous in the way we might imagine. From a mainstream perspective, this is simply the nature of space communication. Distances, even in low Earth orbit, introduce constraints. Bandwidth is limited. Prioritization is necessary. But again, it introduces a layer. The interaction between astronauts and the public is not direct. It is mediated through systems that manage, process, and sometimes filter information. And this is where the pattern becomes almost consistent across every aspect of NASA's operations. Whether it's deep space imagery, Earth observation data, or live feeds from orbit, the public experience is always one step removed from the raw source, not disconnected, just translated. Now, Let's consider something that often goes unnoticed. The ISS, despite being a symbol of continuous human presence in space, operates under strict schedules, protocols, and constraints. Every activity is planned, every resource is monitored. Oxygen levels, temperature, radiation exposure, all carefully controlled. From the mainstream perspective, this level of structure is necessary for safety and efficiency. Space is an unforgiving environment, and precision is essential. But it also means that the station is not just a place of exploration, it is a highly managed system. And in highly managed systems, unpredictability is minimized. Variables are controlled. Outcomes are monitored closely. Which leads to an interesting thought. How much of what happens aboard the ISS is exploratory, and how much is confirmatory? In other words, are experiments primarily designed to discover the unknown, or to validate models that already exist? The answer, of course, is both. Science progresses through a combination of exploration and verification, but the balance between those two can shape what kinds of discoveries are made and which ones are emphasized. Now, none of this suggests that the ISS is hiding something or presenting an inaccurate picture. Instead, it highlights a broader theme that has been quietly unfolding throughout this discussion. NASA operates in environments where direct experience is limited, and so it relies on systems of observation, interpretation, and communication. And those systems, while highly advanced, are still human constructs. They are designed to make the unknown understandable, but in doing so, they inevitably shape how the unknown is perceived. So as we continue, what we're really beginning to see is not a series of isolated questions, but a consistent framework. Observation, translation, presentation. And within that framework, there is always a space, small but present, where interpretation lives. And it is in that space that the most interesting questions tend to form. Not because something is wrong, but because something is incomplete. As we move deeper into this, it becomes useful to step slightly away from the hardware, the missions, the stations in orbit, and focus instead on something less visible, but arguably just as influential. Because behind every image, every broadcast, every dataset we've talked about so far, there is another layer quietly shaping how all of it is understood. Communication. Not just the act of sending information, but the way that information is structured, framed, and delivered to the public. Because if NASA is the observer of space, it is also, in many ways, the narrator of it. And narration, even when it is accurate, always involves choices. From a mainstream perspective, NASA's communication strategy is designed to inform and educate. Press releases, public briefings, scientific publications, educational outreach, these are all part of a system meant to make complex ideas accessible. And by most measures, it has been remarkably successful. Generations of scientists, engineers, and curious minds have been inspired by the way NASA presents its work. But inspiration is not the same as raw information. And that distinction, while subtle, is where things begin to get interesting. Because when NASA communicates a discovery, whether it's a new exoplanet, a distant galaxy, or a pattern in Earth's climate, it doesn't present every detail simultaneously. It can't. The data is too complex, too layered, so it is distilled. Key points are highlighted. Narratives are built around findings. Visuals are selected to reinforce understanding. And again, this is necessary. Without it, the information would be overwhelming. But it also means that what the public receives is not the full data set. It is the interpreted version of it. Now, let's consider how this plays out over time. Certain ideas become familiar. Black holes, for example, are now almost common knowledge. The concept of space-time curvature, once highly abstract, is now widely discussed in simplified terms. The idea of galaxies, nebulae, cosmic expansion, these have become part of a shared understanding of the universe. From a mainstream standpoint, this is progress, knowledge becoming more accessible. But from another angle, it also means that these ideas have been shaped into forms that are easier to communicate. And in that process, some complexity is inevitably reduced. Now, reducing complexity isn't inherently problematic. It's often necessary for learning. But it does create a situation where the public understanding of a concept may differ slightly from the full scientific picture. Not incorrectly, but incompletely. And this brings us to a quieter, more structural observation. NASA doesn't just communicate discoveries, it sets the tone for how those discoveries are interpreted globally. Media outlets, educational systems, even independent researchers often rely on NASA's framing as a starting point, which means that the way NASA tells a story can influence how that story is told everywhere else. Now, let's take a specific example. When NASA announces a discovery, say, evidence of water on Mars or an Earth-like exoplanet, the initial communication often emphasizes the most compelling aspect of the finding. Headlines form quickly, the idea spreads. Water found. Potentially habitable. New Earth discovered. From a mainstream perspective, these summaries are accurate within context. They reflect real observations. But the full details are usually more nuanced. Water might exist in trace amounts, bound within minerals, or present under very specific conditions. Habitability might be theoretical, based on distance from a star rather than actual environmental measurements. And again, this isn't misleading, it's a matter of scale. The headline captures attention, the details require deeper reading. But over time, this pattern creates something subtle, a version of space exploration that feels more definitive, more complete than it actually is. Because the uncertainties, the margins of error, the unresolved questions, these tend to exist in the background, while the clearer narrative moves to the forefront. Now, this isn't unique to NASA, it's a feature of communication in general, but in a field where direct verification is limited for most people, the effect becomes more pronounced. Because for many, NASA's narrative is the only narrative they encounter. And that leads to an interesting question. If the public primarily experiences space through curated communication, how does that shape the boundaries of what is considered possible, or even thinkable? Because once a framework is established, once certain ideas become accepted, it can become more difficult to step outside of that framework, even when new data suggests alternative interpretations. Not impossible, but less immediate. And this is where the idea of unknown unknowns begins to surface. Not things that are hidden, but things that are simply not emphasized. Not because they are unimportant, but because they are difficult to communicate clearly. For example, anomalies in data, unexpected readings, patterns that don't fit neatly into existing models. In scientific circles, these are often discussed, debated, investigated. But in public communication, they may appear only briefly, or not at all, unless they lead to a clear conclusion. Which makes sense. Communicating uncertainty is challenging. It can be misunderstood, misinterpreted. But it also means that the public-facing story of space exploration tends to be smoother, more resolved than the underlying process actually is. And once again, we return to the same structure we've been tracing from the beginning: observation, interpretation, communication. At each step, clarity increases, but so does the distance from the raw complexity of the original data. Now, none of this suggests that NASA is intentionally shaping a misleading narrative. It suggests something more natural. That in the process of making the universe understandable, certain aspects become more visible than others. And over time, those visible aspects become the story we recognize. So as we continue, what we're really beginning to explore is not just NASA's missions or technologies, but the framework through which reality itself is presented to us. Because when the subject is something as vast and distant as space, the way it is described becomes almost as important as the observations themselves. And sometimes, the most revealing questions are not about what is being said, but about what is left unsaid. Not hidden, just quiet. As we continue, it becomes useful to turn our attention towards something that sits quietly at the edge of nearly everything NASA studies. Something that is rarely seen directly, yet constantly referenced as if it is firmly understood. Not a spacecraft, not a mission, but a concept. One that has become so familiar that it almost feels concrete, even though it exists almost entirely in the realm of inference. Dark matter and dark energy. From a mainstream scientific perspective, these are not speculative ideas in the casual sense. They are proposed explanations for very real, very measurable phenomena. When astronomers observe galaxies, they notice something unusual. The outer edges rotate at speeds that don't match the amount of visible mass present. According to known physics, those galaxies should be flying apart, and yet they remain stable. The solution proposed by modern astrophysics is dark matter, an unseen form of mass that exerts gravitational influence but does not interact with light in a detectable way. Similarly, when scientists observe the expansion of the universe, they find that it is not slowing down as expected, but accelerating. The explanation for this is dark energy, a kind of force or property of space itself that drives this acceleration. These ideas are widely accepted within the scientific community because they consistently match observations. Models that include dark matter and dark energy align with the data far better than models that do not, and that's the mainstream understanding. But what makes these concepts particularly interesting in the context of everything we've been discussing is how they are known. Because they are not observed directly. They are inferred. Their existence is concluded from the behavior of other things: stars, galaxies, radiation patterns. They are, in a sense, the invisible framework used to explain visible effects. And NASA, through instruments like the Hubble Space Telescope and the James Webb Space Telescope, plays a significant role in collecting the data that supports these models. From a scientific standpoint, this is entirely valid. Much of science operates this way. Electrons, for example, were understood through their effects long before they were directly observed. But it does introduce a fascinating layer. Because when a large portion of the universe is described using entities that cannot be directly seen, our understanding becomes deeply tied to interpretation. Not just observation, but interpretation of observation. Now, this doesn't make the models incorrect. In fact, they are currently the best explanations available. But it does mean that they are part of an evolving framework. And within that framework, there is room for refinement, or even replacement if new evidence emerges. Now, let's pause here for a moment and consider something that often goes unspoken. Dark matter and dark energy together are estimated to make up the vast majority of the universe, far more than the ordinary matter we can see and interact with, which leads to a simple but profound realization. Most of the universe, as it is currently understood, is not directly observable, and yet we speak about it with a certain level of confidence. Again, this confidence is based on consistent data and well-tested models. It is not arbitrary, but it does highlight something important. That even at the highest levels of scientific understanding, there are elements of reality that are defined more by inference than by direct observation. And this brings us back to NASA's role. Because NASA is not just collecting data, it is contributing to the construction of these models. The observations it provides help shape the theories that describe the universe at its largest scales. And once those theories become widely accepted, they begin to influence how new data is interpreted. This is a natural process in science. Frameworks guide understanding. They provide a structure within which new information can be evaluated. But they can also, at times, limit the range of interpretations that are immediately considered, not intentionally, just structurally, because when a model works well, there is less incentive to question its foundations unless something clearly contradicts it. And that brings us to an interesting point. There have been alternative ideas proposed over time. Modifications to gravity, different interpretations of cosmic expansion, new ways of thinking about large-scale structure. Most of these have not replaced the current models, largely because they do not align with the data as consistently. But their existence highlights something important, that the story of the universe is not finished. It is still being tested, still being refined. And NASA, as one of the primary collectors and interpreters of cosmic data, is deeply embedded in that process. Now let's connect this back to the broader pattern we've been following. When NASA presents findings related to dark matter or dark energy, it does so within the context of current models. Visualizations are created, simulations are shown, concepts are explained in ways that make them accessible. And over time, these explanations become part of the public understanding of the universe. But the underlying reality is more fluid. The models are strong, but not absolute. The data is extensive, but not complete. And the interpretation, while carefully constructed, is still interpretation. So what we begin to see is a layered structure of understanding. At the base, there is observation, light collected by telescopes, measurements recorded by instruments. Above that, there is analysis, patterns identified, models applied. And above that, there is communication, the story that emerges from the data. Each layer is necessary, each adds clarity, but each also adds a degree of separation from the raw, unfiltered reality. And in that separation, there is space for questions, for alternative perspectives, for the possibility that what we understand today is only part of a larger picture. Not wrong, just incomplete. And perhaps that's the most consistent theme we've encountered so far. Not that there are hidden answers waiting to be uncovered, but that the answers we have are part of an ongoing process, a process that is still unfolding. And as we continue, we'll begin to look at how this process extends beyond observation and theory into something even more subtle. The boundaries of what is explored and what is not. As we continue, the focus begins to shift towards something even less obvious. Not what NASA discovers, not how it interprets data, but something more structural, something that sits quietly beneath all of it, shaping the direction of exploration itself. Because every mission, every telescope, every data set we've talked about so far shares one thing in common. It exists because someone decided it should. And that brings us to a question that is rarely asked directly. Not, what has NASA found, but what has NASA chosen to look for? At first, the answer seems simple. NASA explores space. It studies planets, stars, galaxies, Earth systems. Its goals are outlined in public documents, scientific roadmaps, long-term strategies. From a mainstream perspective, these decisions are driven by a combination of scientific curiosity, technological feasibility, and budget constraints. Committees of experts propose missions, priorities are debated, projects are selected based on potential impact and available resources. And this process is, for the most part, transparent. But when you step back and look at it from a slightly wider angle, something subtle begins to emerge. Exploration is not just about discovery, it is about selection. Because for every question NASA chooses to pursue, there are countless others that remain unexplored. Not because they are unimportant, but because resources are limited, time is limited, attention is limited, so choices have to be made. And those choices shape the boundaries of what becomes known. Now, this isn't unique to NASA. It's true of all scientific institutions. But in the context of space exploration, the scale of those choices becomes more significant, because space is vast, almost incomprehensibly so, and the portion of it that we actively study is, by comparison, incredibly small. So when NASA directs its instruments towards certain targets, specific planets, particular regions of space, defined types of phenomena, it is, in effect, defining the areas where knowledge will expand, and by extension, the areas where it won't. Now, from a mainstream standpoint, this is simply a matter of practicality. You can't study everything at once, so you focus on what is most promising, most accessible, most likely to yield meaningful results. And that makes sense. But it also introduces an interesting dynamic, because the criteria used to define promising or meaningful are themselves based on existing frameworks of understanding. In other words, NASA tends to look for answers to questions it already knows how to ask. And that's where things become more nuanced. Because what about the questions that haven't been fully formed yet? The phenomena that don't fit neatly into existing categories? The possibilities that fall outside current models? These are not ignored, but they are harder to prioritize. Not because they lack value, but because they are less defined. And in a system that relies on planning, funding, and measurable outcomes, definition matters. Now, let's bring this into a more concrete context. Consider the search for life beyond Earth. NASA has dedicated significant resources to this question, focusing on environments that resemble conditions where life exists on Earth. Liquid water, certain temperature ranges, chemical signatures associated with biological processes. From a mainstream perspective, this approach is logical. It is based on the only example of life we currently have, our own planet. But it also means that the search is guided by a specific assumption, that life elsewhere would resemble life here, at least in some fundamental ways. And that assumption shapes where we look, what we measure, and how we interpret results. Now, this doesn't mean the assumption is wrong. It's a starting point. But it does raise a quiet question. What if life, or something functionally similar to it, exists in forms that don't match those expectations? Would we recognize it? Or would it exist just outside the boundaries of what we're currently equipped to detect? These are not easy questions to answer, and they're not often emphasized in public discussions because they are by nature speculative. But they are part of the broader landscape of exploration. Now, let's extend this idea beyond biology. There are entire categories of phenomena that remain only partially understood. High-energy cosmic events, unusual signal patterns, anomalies in data that don't immediately resolve into known explanations. In many cases, these are investigated thoroughly within scientific communities. But when it comes to large-scale mission planning, the focus tends to remain on areas where the likelihood of clear, interpretable results is higher. Again, this is practical. But it also means that the edges of understanding, the areas where things are less certain, are explored more cautiously, more selectively. And this brings us back to the structure we've been following. Observation is not random, it is directed. Interpretation is not neutral, it is guided by frameworks. Communication is not exhaustive, it is curated. And within that structure, there are always spaces, small but real, where possibilities exist outside the main narrative. Not hidden, just not prioritized. Now, none of this suggests that NASA is intentionally avoiding certain discoveries or steering away from inconvenient truths. That would be an oversimplification. Instead, it suggests something more grounded. That exploration, especially at this scale, is shaped by human systems. Systems that rely on planning, consensus, and measurable outcomes. And those systems, while highly effective, are not infinite in scope. They have boundaries. So as we continue, what we're beginning to see is that NASA's story is not just about what has been discovered, but about how discovery itself is structured. What questions are asked, what tools are built, what data is collected, and perhaps most importantly, what remains just beyond the edge of focus. Because sometimes the most interesting possibilities are not the ones being actively explored, but the ones that haven't yet been fully considered. As we continue, the direction shifts again, this time towards something that sits quietly between exploration and decision-making, something that influences not just what NASA studies, but how far it is willing to go. Because beyond science, beyond engineering, beyond even curiosity, there is another force shaping everything we've talked about so far. Limitations. Not just technical limitations, but economic, political, and institutional ones. Because while NASA is often viewed as a purely scientific organization, it is, in reality, something more complex. It is a government agency, operating within a system that requires funding, approval, and alignment with broader national priorities. From a mainstream perspective, this is well understood. NASA's budget is determined through political processes. Missions are proposed, reviewed, and approved based not only on their scientific value, but also on their cost, feasibility, and relevance to current objectives. And this system, in many ways, ensures accountability. Large-scale projects require oversight. Resources must be allocated responsibly. But when you look at it more closely, it introduces an interesting dynamic. Because the direction of exploration is not determined solely by what is scientifically possible, but also by what is considered justifiable. And justification, especially in a political context, often requires clarity, measurable goals, predictable outcomes, tangible benefits. Which brings us back to something we touched on earlier. The unknown is difficult to justify. If a mission is designed to answer a well-defined question, measure a specific parameter, test a particular hypothesis, it is easier to support. The expected outcomes can be explained. The risks can be assessed. But if a mission is aimed at something less defined, exploring anomalies, investigating phenomena that don't yet have clear frameworks, it becomes harder to present. Not impossible, but more uncertain. And uncertainty, in systems that depend on approval and funding, tends to be approached carefully. Now, from a mainstream standpoint, this is simply responsible planning. Resources are limited, so they are directed toward areas where the likelihood of meaningful results is higher. But it also means that exploration is, in a sense, guided toward the predictable. Not because unpredictability is avoided entirely, but because it is more difficult to structure. And this creates a subtle boundary, not a barrier, but a gradient. On one side, well-defined scientific objectives with clear methodologies. On the other, open-ended questions that are harder to frame within existing systems. And NASA, operating within these constraints, tends to move along that gradient carefully. Now, let's bring this into a more concrete example. Human spaceflight. After the Apollo program, there was a noticeable shift in how NASA approached crewed missions. Instead of continuing deeper into space, toward Mars for example, the focus moved toward low Earth orbit, leading to programs like the Space Shuttle and later the International Space Station. From a mainstream perspective, this shift was practical. The cost of deep space missions was immense. The risks were high. Developing reusable systems and maintaining a continuous presence in orbit provided long-term scientific and technological benefits. And that reasoning holds up, but it also reflects something broader, a preference for environments where variables can be controlled more effectively. Low Earth orbit, while still challenging, is far more accessible than the Moon or Mars. Communication delays are minimal. Resupply missions are possible. Emergency scenarios, while serious, are more manageable. In other words, it is a space where exploration can be sustained within known limits. Now compare that to deep space missions, long-duration travel, significant communication delays, limited opportunities for intervention, higher levels of uncertainty. These are not insurmountable challenges, but they are more difficult to frame within systems that require predictability. And so progress toward those goals tends to be slower, more incremental. Again, this is not a flaw. It is a reflection of how complex systems operate. But it does highlight something important. The pace and direction of exploration are influenced not just by what we can do, but by what we can support. Now let's take this idea one step further. Public perception. NASA does not operate in isolation. Its work is funded by the public, and public interest plays a role in shaping priorities. Missions that capture imagination, Mars exploration, asteroid defense, the search for life, often receive more attention, and at times, more support. From a mainstream standpoint, this is part of the relationship between science and society. Engagement drives funding, and funding enables discovery. But it also means that certain narratives become more prominent, stories that are easier to understand, easier to communicate, easier to visualize. And over time, these narratives can influence which areas of exploration are emphasized, not because other areas are unimportant, but because they are less visible. Now, when you combine all of these factors, budget constraints, political oversight, public perception, you begin to see a more complete picture. NASA's exploration is not just guided by curiosity, it is shaped by systems that are logical, necessary, and effective, but also structured. And within that structure, there are boundaries, not rigid ones, but real ones. Boundaries that define how far, how fast, and in what direction exploration moves. So as we continue, what we're really uncovering is not a hidden narrative, but a layered one. A story where science, engineering, communication, and human systems all intersect. And within that intersection, there is always a balance between certainty and uncertainty, between exploration and limitation, between what is known and what is still just beyond reach. And perhaps the most interesting part is not where those boundaries are, but how they shift over time. Because every now and then, something changes. A new technology, a new discovery, a new question that becomes clear enough to pursue. And when that happens, the boundary moves, just a little. As we continue, the focus begins to settle into something even quieter, something that isn't tied to a single mission, a specific discovery, or even a particular decade. Instead, it lives in the background of everything we've explored so far, a kind of underlying rhythm that shapes how NASA evolves over time. Because if you look closely, NASA's history is not a straight line of continuous progress. It moves in phases, periods of intense activity, followed by stretches that feel slower, more deliberate. Moments where breakthroughs seem to happen rapidly, and others where advancement appears to pause, or even step sideways. From a mainstream perspective, This pattern is expected. Large-scale scientific and engineering efforts don't progress evenly. They depend on funding cycles, technological readiness, political priorities, and shifting global contexts. The transition from the Apollo program to the Space Shuttle and then to the International Space Station reflects these kinds of shifts. Each phase has its own goals, its own constraints, its own definition of success. And when viewed through that lens, the pattern makes sense. But when you step back a little further, when you look at the overall timeline as a whole, something more subtle begins to appear. The transitions between these phases are not always smooth. They involve gaps, not just in time, but in momentum. After the final Apollo mission, for example, there was no immediate continuation of deep space human exploration. The focus changed, the direction shifted, and for decades, the idea of returning to the moon, or going beyond it, remained more conceptual than operational. From a mainstream standpoint, this is explained by practical realities. Budgets were reduced, public interest evolved, the goals of the agency were redefined. All of that is true, but it also highlights something deeper. That progress, especially at this scale, is not just about capability, it's about continuity. And continuity is fragile, because even if the knowledge exists, even if the technology has been developed, maintaining that capability requires sustained effort. Skilled teams, manufacturing infrastructure, institutional memory, and when that continuity is interrupted, even briefly, rebuilding it can take years, sometimes decades. Now, this is not unique to NASA. It's a characteristic of any complex system. But in the context of space exploration, where each step builds on the last, the effect becomes more pronounced. Because the distance between where we are and where we want to go is so vast. Now, let's take this idea and look at it from a slightly different angle. Technological capability versus operational reality. It is one thing to develop a system that works, to prove that something is possible. It is another to sustain that system, to make it repeatable, scalable, reliable over time. The Saturn V rocket, for example, remains one of the most powerful launch vehicles ever built. It successfully carried humans to the moon multiple times. From a purely technical standpoint, it demonstrated that deep space human missions were achievable. And yet, that capability was not maintained in a continuous way. The reasons, again, are practical: cost, complexity, shifting priorities. But it creates an interesting contrast. The peak of capability, followed by a long period where that specific capability was no longer active, not lost entirely, but not in use. And this brings us back to the idea of phases. NASA's history can be seen as a series of peaks and plateaus, moments where certain capabilities are pushed to their limits, followed by periods where those capabilities are consolidated, restructured, or redirected. From a mainstream perspective, this is strategic. It allows for reflection, improvement, and adaptation. But it also means that progress is not always cumulative in a straightforward way. Sometimes it resets. Not completely, but enough to require rebuilding. Now let's connect this to something broader: the perception of progress. From the outside, it can feel like humanity reached a certain point, landing on the moon, and then stepped back, as if the trajectory paused or slowed more than expected. But from the inside, the picture is more complex. Advancements continued, just in different areas. Satellite technology, robotic exploration, space-based observation. The focus shifted from reaching new destinations to understanding existing ones more deeply. And that shift, while less dramatic, was still significant. But because it was less visible, less iconic, it changed how progress was perceived. Which brings us to another subtle layer: visibility. Not all achievements are equally visible. Some capture global attention, others unfold quietly, over long periods of time, without a single defining moment. And NASA, like any organization, operates across both of these modes: high visibility milestones and low visibility accumulation. Now here's where things become particularly interesting. When visibility decreases, interpretation becomes more open. In the absence of a clear, singular narrative, like the moon landings, people begin to fill in the gaps with their own perspectives. Questions emerge, curiosity expands, not necessarily because something is missing, but because something is less defined. And that brings us back to the pattern we've been following from the beginning: observation, interpretation, communication. But now, with an added dimension: time. Because over time, the way information is presented, the pace at which discoveries are made, the visibility of progress, all of these factors influence how the story is understood. And sometimes, the gaps between phases, the pauses, the transitions, become just as interesting as the phases themselves. Not because they indicate something hidden, but because they reveal how complex the process of exploration really is. So as we continue, what we're beginning to see is not just a story of discovery, but a story of rhythm, periods of acceleration, followed by periods of recalibration, moments where the boundaries of the known expand rapidly, and others where those boundaries are quietly redefined. And within that rhythm, there is always a sense of something just ahead, something not yet fully reached. Not because it is out of reach, but because the path toward it is still being shaped. As we continue, the perspective shifts once more, this time towards something even more subtle, something that doesn't immediately appear in mission summaries or scientific papers, but quietly influences how everything we've explored is ultimately understood. Trust. Not in the simple sense of believing or doubting, but in the deeper sense of how knowledge is accepted when direct verification isn't possible. Because when it comes to space, whether it's distant galaxies, orbital stations, or even data about our own planet, most people rely on systems they cannot personally access. And at the center of that system, consistently, is NASA. From a mainstream perspective, this trust is well earned. NASA collaborates with international agencies, publishes research, provides data to independent scientists, and operates within a framework that includes peer review and external validation. Observatories around the world confirm many of its findings. Other space agencies, like ESA and JAXA, produce data that aligns with NASA's observations. In other words, there is a network of verification, and that network is one of the strongest arguments in favor of the reliability of modern space science. But even within that network, the structure remains the same. Data is collected by specialized instruments. It is processed through complex systems. It is interpreted using established models. And then it is communicated outward. At each step, expertise increases, but accessibility decreases. Which means that, for most people, understanding depends on trust in those who operate within that system. Now, trust in science is not blind. It is built over time, through consistency, through successful predictions, through the ability to explain phenomena in ways that can be tested and replicated. And NASA, over decades, has contributed significantly to that foundation. But trust also has another dimension, one that is less often discussed. It shapes what questions are asked. Because when a system is trusted, its outputs are less likely to be questioned at a fundamental level. not ignored entirely, but accepted as a reliable starting point. And in most cases, that is both reasonable and efficient. But it also means that certain assumptions can become deeply embedded. Not because they are incorrect, but because they are rarely challenged outside of specialized circles. Now, let's pause here and consider something that often goes unnoticed. The difference between questioning a conclusion and questioning a framework. Science encourages the first, individual results, specific findings, particular interpretations. These are constantly tested, debated, refined. But the broader framework, the underlying structure that defines how questions are asked and how answers are interpreted, changes more slowly. Not because it is fixed, but because it is foundational, and NASA operates within that framework. It contributes to it, reinforces it, and occasionally helps reshape it. But it does not exist outside of it. Now, this is not a limitation. It is how large-scale knowledge systems function. But it does mean that the way NASA explores and explains the universe is influenced by the current boundaries of understanding. And those boundaries, while expansive, are not infinite. So when new data is encountered, it is often interpreted in a way that fits within existing models, at least initially. And most of the time, this works. But occasionally, there are moments where the fit is less precise, where observations raise questions that are not immediately resolved. In those moments, the system adapts, models are adjusted, new theories are proposed, but the process takes time, and during that time, the public-facing narrative often remains stable. Not because change is resisted, but because it is gradual. Now, let's connect this back to the idea of trust. When the narrative remains stable, trust is reinforced. Consistency builds confidence. But it can also create the impression that understanding is more complete than it actually is, that the edges of knowledge are further away than they really are. And this is where things become particularly interesting, because the edges are still there, in every data set that contains unexplained anomalies, in every model that requires assumptions to function, in every observation that leads to more questions than answers. These edges are not failures. They are the natural boundaries of exploration, but they are not always visible in the simplified versions of the story. And so, for most people, the universe appears more defined, more settled, more understood than it truly is. Now, none of this suggests that NASA is presenting an inaccurate picture. It suggests that the picture, by necessity, is incomplete. Not because information is withheld, but because complexity cannot be fully conveyed in a single layer of communication. So what we begin to see is a dual reality. On one level, a clear, structured understanding of space, planets, stars, galaxies, all described within well-established frameworks. On another level, a much more fluid landscape, one where questions remain open, where models continue to evolve, where uncertainty is an ongoing presence, and NASA exists at the intersection of these two levels, translating one into the other, making the complex accessible, while continuing to navigate the unknown. So as we move forward, what we're really exploring is not just the information NASA provides, but the space around that information, the areas where certainty fades into possibility, not because something is hidden, but because something is still unfolding. And perhaps that's the most important realization so far, that even with all the data, all the technology, all the decades of exploration, we are still, in many ways, at the beginning. As we continue, the focus begins to drift towards something even more subtle, something that doesn't sit in the data itself, or the missions, or even the frameworks we've been exploring, but rather in the relationship between all of them. Because up to this point, we've looked at how NASA observes, interprets, communicates, and decides what to explore. But now, it becomes worth asking a slightly different kind of question. Not just how NASA shapes our understanding of space, but how that understanding, once formed, begins to shape us. Because over time, the information NASA provides doesn't just remain as isolated knowledge. It becomes part of a larger cultural and intellectual landscape. It influences how people think about the universe, about humanity's place within it, and even about what is considered possible. From a mainstream perspective, this is one of NASA's greatest contributions. It expands perspective. It moves humanity beyond a purely Earth-centered view. It introduces scales of distance and time that are almost impossible to grasp fully, yet fundamentally change how we see reality. Images of distant galaxies, data about the age of the universe, the understanding that we are part of a vast and dynamic system. These ideas have reshaped modern thought in profound ways, and importantly, they are grounded in science. But there is another layer to this influence, one that is less about the content of the information and more about its structure. Because when knowledge is consistently presented through a particular framework, that framework becomes familiar. It becomes the default way of interpreting new information, and over time, it becomes almost invisible. Now, this isn't unique to NASA. It's how all systems of knowledge work. Frameworks provide stability. They allow for cumulative understanding, but they can also, quietly, define the limits of what feels intuitive. For example, consider how we now think about the universe. Concepts like billions of light years, expanding space, invisible forces shaping cosmic structures. These ideas, once abstract, are now widely accepted, and they are supported by evidence, but they are also presented within a specific interpretive structure, a structure that organizes observations into coherent models. And once that structure becomes familiar, it begins to guide how new observations are understood, not in a restrictive way, but in a directional one. Now let's take this a step further. When NASA presents a new discovery, it is almost always framed within existing models. A newly observed phenomenon is explained in terms of known physics, known processes, known categories. And this makes sense. It provides clarity. It connects the new information to what is already understood. But it also means that truly unfamiliar interpretations, those that don't fit easily into existing frameworks, can be more difficult to recognize immediately, not because they are dismissed, but because they are harder to define. And this brings us to an interesting point. Innovation in science often happens at the edges of frameworks, not within them. It occurs when something doesn't quite fit, when an observation resists easy explanation, when a pattern emerges that challenges existing assumptions. And in those moments, the framework itself begins to shift. But those moments are rare and they take time, because frameworks, once established, are powerful. They organize vast amounts of information. They provide consistency. They allow for prediction and verification. And NASA, as one of the primary contributors to our understanding of space, operates deeply within these frameworks. It helps build them, refine them, and occasionally expand them. Now let's connect this back to the broader theme we've been following. Throughout this exploration, we've seen how information moves, from observation to interpretation to communication. We've seen how decisions shape what is studied, how limitations influence what is possible, how trust supports the entire system. And now, we're seeing how all of that feeds back into perception. Because once a narrative is established, once a way of understanding the universe becomes widely accepted, it begins to shape the questions that come next. Not consciously, but naturally. People ask questions that fit within the framework they know. They explore possibilities that seem consistent with what they've learned, and in doing so, they extend the framework, rather than stepping outside of it. Again, this is not a flaw, it is how knowledge grows. But it does mean that there is always a layer of reality that exists just beyond the current frame of reference, not hidden, just not yet fully conceptualized. Now, consider what this means in the context of NASA's role. NASA is not just exploring space, it is helping define how space is understood. And that understanding, in turn, influences future exploration. It's a feedback loop. Observation informs interpretation. Interpretation shapes communication. Communication influences perception. Perception guides new questions, which lead back to observation. And around it goes. Now, within that loop, there is always stability, but also the potential for change. Because every so often, something unexpected appears. A signal that doesn't match predictions. A measurement that challenges assumptions. A discovery that opens more questions than it answers. And when that happens, the loop adjusts. Slowly, carefully, sometimes almost imperceptibly. But it adjusts. And those adjustments are where the most significant shifts in understanding tend to occur. Not suddenly, but gradually. So as we continue, what we're really approaching is the edge of this entire system. The point where observation, interpretation, communication, and perception all begin to blur together. Where the distinction between what is known and what is believed becomes less clear. Not because they are the same, but because they are closely connected. And in that space, there is always something just beyond reach. Not because it is being kept there, but because it has not yet been fully brought into focus. As we continue, everything we've explored so far begins to settle into a broader perspective, one that is less about any single mission, discovery, or decision, and more about the overall structure of how something as vast as space is turned into something we can understand at all. Because by now, a pattern has quietly repeated itself across every layer: observation, interpretation, communication, limitation, trust, and perception. And when you step back far enough, those layers begin to blend into a single process, a process of translation. And at the center of that process, consistently, is NASA. Not as a gatekeeper, not as something controlling information, but as something far more nuanced. A translator between environments that humans cannot directly experience and minds that are trying to make sense of them. From a mainstream perspective, this is exactly what NASA is meant to do. It builds instruments capable of detecting signals far beyond human senses. It sends machines into places no human can easily reach. It collects data that would otherwise remain inaccessible. And then it turns that data into something structured, something interpretable, something that fits into the broader framework of scientific understanding. And when you look at it this way, the scale of that task becomes almost difficult to grasp. Because translating something requires more than just accuracy. It requires context. Raw data, on its own, is often meaningless without interpretation. A stream of numbers, a set of signals, variations in electromagnetic radiation, these don't inherently tell a story. They have to be processed, compared, modeled, and finally expressed in a way that aligns with what we already know, or at least what we think we know. And that last part is where things become especially interesting, because translation is never perfectly neutral, not because it is biased in an intentional way, but because it must pass through systems, mathematical models, computational methods, human decisions about presentation. Each of these systems is built on existing knowledge, existing assumptions, existing frameworks. And so, what emerges on the other side is not just the original signal, but the signal as understood within those frameworks. Now, from a scientific standpoint, this is not a weakness. It is the only way to make sense of complex information. Without frameworks, data remains disconnected. Without models, patterns cannot be identified. But it does mean that every piece of understanding we have about space exists within a structure that is constantly being tested, refined, and occasionally expanded, but a structure nonetheless. Now, let's slow this down for a moment and look at what that really implies. If every observation is interpreted, if every interpretation is communicated, if every communication is shaped for clarity, then the version of reality we experience is always one step removed from the raw, unfiltered source. Again, not inaccurately removed, but inevitably. And that brings us to a very quiet, but very important realization. There is always more information than what is presented, not hidden, not withheld, just beyond the layer that has been translated into something we can easily understand. Now, this doesn't mean that the missing information would fundamentally change our understanding. In many cases, it would simply add complexity, nuance, additional detail. But occasionally, it might do more than that. It might highlight areas where the current framework is incomplete, where assumptions are being used to bridge gaps, where questions remain open, even if they are not emphasized. And this is where the idea of secrets begins to take on a different meaning. Not secrets in the sense of concealed truths, but in the sense of unresolved edges, places where knowledge fades into uncertainty. Because when people think of secrets, they often imagine something hidden behind intention. But in systems like NASA's, the more interesting secrets are often the ones that exist without intention, the ones that emerge naturally from the limits of understanding. Now, let's connect this back to everything we've seen so far. The moon landings and how they were experienced through layers of technology. Deep space imagery and how it is constructed from wavelengths we cannot see. Earth observation and how data becomes visual interpretation. The ISS and how life in orbit is presented through curated perspectives. Dark matter and dark energy, inferred rather than directly observed. Mission planning, shaped by feasibility and structure. Communication, distilled for clarity. Trust, built on consistency, but dependent on systems. Frameworks, guiding how new information is understood. All of these are not separate topics. They are different expressions of the same underlying process. Translation. And within that process, there is always a boundary. Not a fixed one, but a moving one. A boundary between what has been translated into understanding and what remains just outside of it. And that boundary is where curiosity lives, not in the sense of suspicion, but in the sense of exploration, because the presence of that boundary doesn't mean something is wrong. It means something is still in progress. So as we approach the final parts of this journey, what we're really doing is not trying to uncover hidden answers, but to become more aware of the structure through which answers are formed. To recognize that even in a system as advanced and carefully constructed as NASA's, there is still room for uncertainty. Still room for questions that haven't fully taken shape yet. Still room for possibilities that exist just beyond the current edge of understanding. And perhaps that's the most grounded perspective of all. Not that everything is known, not that everything is unknown, but that we are somewhere in between, always moving, slowly, carefully, toward a clearer picture, while knowing that the picture itself will never be completely finished. As we continue, everything begins to narrow in, not toward a conclusion, but toward a clearer view of the edges we've been circling this entire time. Because by now, the pattern is no longer subtle. It's steady, consistent, almost quiet in the way it repeats across every layer of NASA's work: observation, interpretation, communication, perception. And at the center of that cycle, again, is NASA, not as something mysterious, but as something far more grounded. A system built to extend human perception beyond its natural limits, and then translate what it finds into something we can understand. But now, it becomes useful to look at what happens when that cycle reaches its limits. Because every system, no matter how advanced, eventually encounters boundaries. Not failures, just edges. Points where the data becomes harder to interpret, where signals become weaker, more ambiguous, where models begin to stretch to accommodate observations that don't fit perfectly. And these edges are not rare. They are everywhere once you know how to look for them. From a mainstream scientific perspective, these edges are where progress happens. They represent the frontier of knowledge, the place where new theories are tested, where existing frameworks are refined or occasionally replaced. And that's true. But what's interesting is how these edges are experienced from the outside, because for most people, these boundaries are almost invisible. The public-facing narrative of space exploration tends to focus on clarity, on discoveries that can be explained, visualized, understood. The unresolved questions, the ambiguous data, the competing interpretations. These exist, but often in the background, not hidden, just quieter. And so, the perception of understanding becomes smoother than the reality of it. Now let's slow this down and examine what that really means. When NASA encounters data that doesn't fit neatly into existing models, it doesn't immediately discard those models. It investigates. It tests alternative explanations. It looks for errors, for new variables, for ways to reconcile the observation with what is already known. Most of the time, this process leads to refinement. The model adjusts slightly. The data finds its place within the framework. But occasionally, it doesn't. Occasionally, the discrepancy remains. Not large enough to overturn the entire system, but persistent enough to suggest that something is missing. And these moments, these small, unresolved gaps, are where things become particularly interesting, because they are not dramatic. They don't announce themselves as major discoveries. They don't immediately change the narrative. They simply exist, quietly. Now, within the scientific community, these gaps are often discussed, analyzed, revisited over time. They are part of the ongoing process of understanding. But in broader communication, they tend to be less emphasized. Again, not intentionally, just because they are harder to explain clearly. And this brings us back to something we've touched on before: the difference between a complete picture and a coherent one. NASA, like any organization communicating complex information, aims for coherence. It presents a picture that makes sense, that can be followed, that reflects the current state of knowledge in a structured way. But coherence is not the same as completeness. A coherent picture can still have gaps. And those gaps are not flaws. They are simply the places where knowledge has not yet fully reached. Now, let's take this one step further. What happens when those gaps begin to accumulate? Not in a way that breaks the system, but in a way that slowly increases the level of uncertainty at the edges. In most cases, the system adapts. New data leads to new models. Old assumptions are revised. The framework expands. But this process takes time. And during that time, the public-facing understanding remains relatively stable, which creates an interesting dynamic, a sense of certainty at the center, and a growing complexity at the edges. Now, none of this suggests that NASA is unaware of these dynamics. In fact, the entire scientific process is built around navigating them. but it does highlight something important for anyone observing from the outside. That the story of space exploration is not static. It is not a finished narrative. It is an evolving one, constantly being updated, refined, sometimes quietly restructured. And NASA, as both an observer and a communicator, exists within that evolution. Now, let's connect this back to the idea of secrets, which we introduced at the very beginning. By this point, it becomes clear that the most meaningful secrets are not hidden pieces of information waiting to be revealed. They are the unresolved edges of understanding, the places where data meets uncertainty, where models meet limitation, where questions remain open. And these are not things that can simply be uncovered and explained once and for all. They are part of the process itself, because exploration, at its core, is not about reaching a final answer. It's about moving the boundary, slowly, carefully, step by step. And every time that boundary moves, new edges appear, new questions emerge, new areas of uncertainty take shape. So as we approach the final part, what we're really left with is not a sense of mystery in the traditional sense, but something more grounded, a recognition that even in one of the most advanced systems humanity has built to understand the universe, there is still a horizon, always just ahead. Not because it is being kept there, but because that is where it naturally belongs. As we reach this final part, everything begins to settle into place, not as a conclusion in the traditional sense, but as a clearer view of the landscape we've been slowly moving through. Because what started as a question about NASA, about its missions, its data, its so-called secrets, has gradually unfolded into something much broader, something quieter, something that doesn't rely on hidden truths or dramatic revelations, but instead on understanding how knowledge itself is formed. Because by now, it should feel almost familiar. The way NASA observes environments we cannot directly experience. The way those observations are translated into data. The way that data is interpreted through models and frameworks. The way those interpretations are communicated, carefully, clearly, and necessarily simplified. And finally, the way all of that becomes the reality we carry in our minds. Not false, not misleading, but shaped. And that word, shaped, is perhaps the most important one to sit with. Because everything we know about space, everything we've explored across these parts, exists within that shaping process. The moon landings, grounded in real events but experienced through layers of technology. The deep space images, constructed from wavelengths beyond human sight. The Earth observations, translated into maps and models. The International Space Station, visible yet still mediated through selected perspectives. The concepts of dark matter and dark energy, inferred from effects rather than directly observed. The decisions about which missions to pursue, shaped by systems of funding, feasibility, and priority. The communication of discoveries, structured for clarity and coherence. The trust that supports it all, built over time but dependent on systems most people never see directly. The frameworks that guide interpretation, providing stability while quietly defining boundaries. The edges of knowledge where uncertainty remains, not as a flaw, but as a natural part of exploration. All of these are not separate threads. They are parts of a single process. A process that turns the unknown into the known, step by step, layer by layer. Now, from a mainstream perspective, this is exactly how science is meant to work. There is no contradiction here, no hidden mechanism behind the scenes. It is a system built on observation, verification, and refinement. And it has taken humanity further in understanding the universe than at any point in history. But what makes this perspective valuable is not that it challenges that system, it's that it reveals its structure. Because once you begin to see that structure, something shifts. You start to recognize that knowledge is not just discovered, it is constructed. Not invented, not fabricated, but assembled. Carefully, methodically, through layers of interpretation and communication. And that realization doesn't weaken the value of what we know. If anything, it deepens it. Because it shows just how much effort goes into bridging the gap between reality and understanding. Now, let's come back to the idea we introduced at the very beginning, the idea of secrets. At this point, it should feel different. Less like something hidden behind intention, and more like something that exists naturally at the edges. Because the most meaningful secrets in NASA's story are not concealed pieces of information waiting to be uncovered. They are the unanswered questions, the areas where data is still being interpreted, where models are still being tested, where frameworks are still evolving, and perhaps most importantly, where new questions have not yet fully taken shape. These are not things that can be revealed all at once. They are part of the process itself. Because every time a question is answered, it leads to another. Every time a boundary is pushed outward, a new boundary appears beyond it. And this is not a limitation, it's the defining feature of exploration. Now, as everything quiets down, as the details begin to fade into the background, what remains is something simple, a sense of scale. Not just the scale of the universe, but the scale of the process we use to understand it. Because for all the technology, all the data, all the decades of work, we are still translating, still interpreting, still learning how to see something that was never meant to be easily seen. And maybe that's the most grounded perspective to end on. Not that NASA holds all the answers, not that there are hidden truths waiting just out of reach, but that we are part of an ongoing attempt to understand something far larger than ourselves. An attempt that is careful, structured, and remarkably effective, but still, inevitably, incomplete. And that incompleteness is not something to be suspicious of. It's something to be aware of. Because awareness is what keeps curiosity alive. It's what allows new questions to form, new perspectives to emerge, new boundaries to be explored. So wherever you are, as this comes to an end, the quiet returns, the details settle. Just remember this: the story of space is not finished. It isn't even close. And everything we've talked about tonight, every mission, every image, every idea, is just one layer of a much larger picture, still unfolding, still being shaped, still waiting to be understood. And maybe, in a way, that's what makes it worth exploring at all.